Optical tweezers are scientific instruments that use a highly focused laser beam to provide an attractive or repulsive force, depending on the refractive index mismatch, to physically hold and move microscopic dielectric objects similar to tweezers. Optical tweezers have been particularly successful in studying a variety of biological systems in recent years. History and development. The detection of optical scattering and gradient forces on micron-sized particles was first reported in 1970 by Arthur Ashken, a scientist working at Bell Labs. Years later, Ashken and colleagues reported the first observation of what is now commonly referred to as an optical tweezer, a tightly focused beam of light capable of holding microscopic particles stable in 3 dimensions. One of the authors of this seminal 1986 paper, former United States Secretary of Energy Stephen Chu, would go on to use optical tweezing in his work on cooling and trapping neutral atoms. This research earned Chu the 1997 Nobel Prize in Physics along with Claude Cohen-Tarnowski and William D. Phillips. In an interview, Stephen Chu described how Ashken had first envisioned optical tweezing as a method for trapping atoms. Ashken was able to trap larger particles, but it fell to Chu to extend these techniques to the trapping of neutral atoms utilizing resonant laser light and a magnetic gradient trap. In the late 1980s, Arthur Ashken and Joseph M. Ziedzik demonstrated the first application of the technology to the biological sciences, using it to trap an individual tobacco mosaic virus and Escherichia coli bacterium. Throughout the 1990s and afterwards, researchers like Carlos Bustamante, James Spudic, and Stephen Bloch pioneered the use of optical trap force spectroscopy to characterize molecular-scale biological motors. These molecular motors are ubiquitous in biology, and are responsible for locomotion and mechanical action within the cell. Optical traps allowed these biophysicists to observe the forces and dynamics of nanoscale motors at the single molecule level. Optical trap force spectroscopy has since led to greater understanding of the stochastic nature of these force-generating molecules. Optical tweezers have proven useful in other areas of biology as well. For instance, in 2003 the techniques of optical tweezers were applied in the field of cell sorting. By creating a large optical intensity pattern over the sample area, cells can be sorted by their intrinsic optical characteristics. Optical tweezers have also been used to probe the cytoskeleton, measure the viscoelastic properties of biopolymers, and study cell motility. A biomolecular assay in which clusters of ligand-coated nanoparticles are both optically trapped and optically detected after target molecule-induced clustering was proposed in 2011 and experimentally demonstrated in 2013. The Capizzo-Dirac effect effectively demonstrated during 2001 uses standing waves of light to affect a beam of particles. Researchers have also worked to convert optical tweezers from large, complex instruments to smaller, simpler ones, for use by those with smaller research budgets. Physics = General description = Optical tweezers are capable of manipulating nanometer and micron-sized dielectric particles by exerting extremely small forces via a highly focused laser beam. The beam is typically focused by sending it through a microscope objective. The narrowest point of the focused beam, known as the beam waist, contains a very strong electric field gradient. Dielectric particles are attracted along the gradient to the region of strongest electric field, which is the center of the beam. The laser light also tends to apply a force on particles in the beam along the direction of beam propagation. This is due to conservation of momentum. Photons that are absorbed or scattered by the tiny dielectric particle impart momentum to the dielectric particle. This is known as the scattering force and results in the particle being displaced slightly downstream from the exact position of the beam waist, as seen in the figure. Optical traps are very sensitive instruments and are capable of the manipulation and detection of sub-nanometer displacements for sub-micron dielectric particles. For this reason, they are often used to manipulate and study single molecules by interacting with a bead that has been attached to that molecule. DNA and the proteins and enzymes that interact with it are commonly studied in this way. For quantitative scientific measurements, most optical traps are operated in such a way that the dielectric particle rarely moves far from the trap center. The reason for this is that the force applied to the particle is linear with respect to its displacement from the center of the trap as long as the displacement is small. In this way, an optical trap can be compared to a simple spring, which follows Hooke's law. Detailed view proper explanation of optical trapping behavior depends upon the size of the trapped particle relative to the wavelength of light used to trap it. In cases where the dimensions of the particle are much greater than the wavelength, a simple ray optics treatment is sufficient. If the wavelength of light far exceeds the particle dimensions, the particles can be treated as electric dipoles in an electric field. For optical trapping of dielectric objects of dimensions within an order of magnitude of the trapping beam wavelength, the only accurate models involve the treatment of either time-dependent or time-harmonic Maxwell equations using appropriate boundary conditions. Ray optics. In cases where the diameter of a trapped particle is significantly greater than the wavelength of light, the trapping phenomenon can be explained using ray optics. As shown in the figure, individual rays of light emitted from the laser will be refracted as it enters and exits the dielectric bead. As a result, the ray will exit in a direction different from which it originated. Since light has a momentum associated with it, this change in direction indicates that its momentum has changed. Due to Newton's third law, there should be an equal and opposite momentum change on the particle. Most optical traps operate with a Gaussian beam profile intensity. In this case, if the particle is displaced from the center of the beam, as in the right part of the figure, the particle has a net force returning it to the center of the trap because more intense beams impart a larger momentum change towards the center of the trap than less intense beams, which impart a smaller momentum change away from the trap center. The net momentum change, or force, returns the particle to the trap center. If the particle is located at the center of the beam, then individual rays of light are refracting through the particle symmetrically, resulting in no net lateral force. The net force in this case is along the axial direction of the trap, which cancels out the scattering force of the laser light. The cancellation of this axial gradient force with the scattering force is what causes the bead to be stably trapped slightly downstream of the beam waist. The standard tweezers works with the trapping laser propagated in the direction of gravity and the inverted tweezers works against gravity. Electric dipole approximation, in cases where the diameter of a trapped particle is significantly smaller than the wavelength of light, the conditions for Rayleigh scattering are satisfied and the particle can be treated as a point dipole in an inhomogeneous electromagnetic field. The force applied on a single charge in an electromagnetic field is known as the Lorentz force. The force on the dipole can be calculated by substituting two terms for the electric field in the equation above, one for each charge. The polarization of a dipole is where is the distance between the two charges. For a point dipole, the distance is infinitesimal, taking into account that the two charges have opposite signs, the force takes the form. Notice that the cancel out. Multiplying through by the charge, converts position, into polarization. Where in the second equality, it has been assumed that the dielectric particle is linear. In the final steps, two equalities will be used, a vector analysis equality, one of Maxwell's equations. First, the vector equality will be inserted for the first term in the force equation above. Maxwell's equation will be substituted in for the second term in the vector equality. Then the two terms which contain time derivatives can be combined into a single term. The second term in the last equality is the time derivative of a quantity that is related through a multiplicative constant to the Poynting vector, which describes the power per unit area passing through a surface. Since the power of the laser is constant when sampling over frequencies much shorter than the frequency of the laser's light 10-14 Hz, the derivative of this term averages to zero and the force can be written as. Where in the second part we have included the induced dipole of a spherical dielectric particle, whereas the particle radius is the index of the medium and is the relative index of the particle. The square of the magnitude of the electric field is equal to the intensity of the beam as a function of position. Therefore, the result indicates that the force on the dielectric particle, when treated as a point dipole, is proportional to the gradient along the intensity of the beam. In other words, The gradient force described here tends to attract the particle to the region of highest intensity. In reality, the scattering force of the light works against the gradient force in the axial direction of the trap, resulting in an equilibrium position that is displaced slightly downstream of the intensity maximum. Under the Rayleigh approximation, we can also write the scattering force as. Since the scattering is isotropic, the net momentum is transferred in the forward direction. On the quantum level, we picture this as incident photons all traveling in the forward direction and being scattered isotropically. By conservation of momentum, the sphere must accumulate the photon's original momenta, causing a forward force. Harmonic potential approximation. A useful way to study the interaction of an atom in a Gaussian beam is to look at the harmonic potential approximation of the intensity profile the atom experiences. In the case of the two-level atom, the potential experienced is related to its AC Stark shift. Whereas the natural line width of the excited state, is the electric dipole coupling, is the frequency of the transition, and is the defining or difference between the laser frequency and the transition frequency. The intensity of a Gaussian beam profile is characterized by the wavelength, minimum waist, and power of the beam. The following formulas define the beam profile. To approximate this Gaussian potential in both the radial and axial directions of the beam, the intensity profile must be expanded to second order and infinite respectively and equated to the harmonic potential. These expansions are evaluated assuming fixed power. This means that when solving for the harmonic frequencies, the frequencies are given as, so that the relative trap frequencies for the radial and axial directions is a function of only beam waist scale as. Setups. The most basic optical tweezer setup will likely include the following components: a laser, a beam expander, some optics used to steer the beam location in the sample plane, a microscope objective and condenser to create the trap in the sample plane, a position detector to measure beam displacements and a microscope illumination source coupled to a CCD camera. An ND/YAG laser is a common choice of laser for working with biological specimens. This is because such specimens have a low absorption coefficient at this wavelength. A low absorption is advisable so as to minimize damage to the biological material, sometimes referred to as opticution. Perhaps the most important consideration in optical tweezer design is the choice of the objective. A stable trap requires that the gradient force, which is dependent upon the numerical aperture of the objective, be greater than the scattering force. Suitable objectives typically have an NA between 1.2 and 1.4. While alternatives are available, perhaps the simplest method for position detection involves imaging the trapping laser exiting the sample chamber onto a quadrant photodiode. Lateral deflections of the beam are measured similarly to how it is done using atomic force microscopy. Expanding the beam emitted from the laser to fill the aperture of the objective will result in a tighter, diffraction-limited spot. While lateral translation of the trap relative to the sample can be accomplished by translation of the microscope slide, most tweezer setups have additional optics designed to translate the beam to give an extra degree of translational freedom. This can be done by translating the first of the two lenses labeled as beam steering in the figure. For example, translation of that lens in the lateral plane will result in a laterally deflected beam from what is drawn in the figure. If the distance between the beam steering lenses and the objective is chosen properly, this will correspond to a similar deflection before entering the objective and a resulting lateral translation in the sample plane. The position of the beam waist, that is the focus of the optical trap, can be adjusted by an axial displacement of the initial lens. Such an axial displacement causes the beam to diverge or converge slightly, the end result of which is an axially displaced position of the beam waist in the sample chamber. Visualization of the sample plane is usually accomplished through illumination via a separate light source coupled into the optical path in the opposite direction using dichroic mirrors. This light is incident on a CCD camera and can be viewed on an external monitor or used for tracking the trapped particle position via video tracking. Alternative laser beam modes The majority of optical tweezers make use of conventional TEMO Gaussian beams. However, a number of other beam types have been used to trap particles, including high-order laser beams, that is Hermite Gaussian beams, Laguerre Gaussian beams and Bessel beams. Optical tweezers based on Laguerre Gaussian beams have the unique capability of trapping particles that are optically reflective and absorptive. Laguerre Gaussian beams also possess a well-defined orbital angular momentum that can rotate particles. This is accomplished without external mechanical or electrical steering of the beam. Both zero and higher-order Bessel beams also possess a unique tweezing ability. They can trap and rotate multiple particles that are millimeters apart and even around obstacles. Micromachines can be driven by these unique optical beams due to their intrinsic rotating mechanism due to the spin and orbital angular momentum of light. Multiplexed optical tweezers equals, a typical setup uses one laser to create one or two traps. Commonly, two traps are generated by splitting the laser beam into two orthogonally polarized beams. Optical tweezing operations with more than two traps can be realized either by time-sharing a single laser beam among several optical tweezers, or by diffractively splitting the beam into multiple traps. With acousto-optic deflectors or galvanometer-driven mirrors, a single laser beam can be shared among hundreds of optical tweezers in the focal plane, or else spread into an extended one-dimensional trap. Specially designed diffractive optical elements can divide a single input beam into hundreds of continuously illuminated traps in arbitrary three-dimensional configurations. The trap-forming hologram also can specify the mode structure of each trap individually, thereby creating arrays of optical vortices, optical tweezers, and holographic line traps, for example. When implemented with a spatial light modulator, such holographic optical traps also can move objects in three dimensions. Single-mode optical fibers equals, the standard fiber optical trap relies on the same principle as the optical trapping, but with a Gaussian laser beam delivered through an optical fiber. If one end of the optical fiber is molded into a lens-like facet, the nearly Gaussian beam carried by a single-mode standard fiber will be focused at some distance from the fiber tip. The effective numerical aperture of such assembly is usually not enough to allow for a full 3D optical trap but only for a 2D trap. A true 3D optical trapping based on a single fiber, with a trapping point which is not in nearly contact with the fiber tip, has been realized based on a not standard annular core fiber arrangement and a total internal reflection geometry. On the other hand, if the ends of the fiber are not molded, the laser exiting the fiber will be diverging and thus a stable optical trap can only be realized by balancing the gradient and the scattering force from two opposing ends of the fiber. The gradient force will trap the particles in the transverse direction, while the axial optical force comes from the scattering force of the two counter-propagating beams emerging from the two fibers. The equilibrium Z position of such a trapped bead is where the two scattering forces equal each other. This work was pioneered by A. Constable al., Opt. Let 18, 1867, and followed by J. Guck al., Phys. Reverend Let 84, 5451, who made use of this technique to stretch microparticles. By manipulating the input power into the two ends of the fiber, there will be an increase of optical stretching that can be used to measure viscoelastic properties of cells, with sensitivity sufficient to distinguish between different individual cytoskeletal phenotypes. That is human erythrocytes and mouse fibroblasts. A recent test has seen great success in differentiating cancerous cells from non-cancerous ones from the two opposed, non-focused laser beams. Multimode fiber-based traps equals. While earlier version of fiber-based laser traps exclusively used single-mode beams, M. Krasing and colleagues recently showed that the careful excitation of further optical modes in a short piece of optical fiber allows the realization of non-trivial trapping geometries. By this the researchers were able to orient various human cell types on a microscope. The main advantage of the so-called optical cell rotator technology over standard optical tweezers is the decoupling of trapping from imaging optics. This, its modular design, and the high compatibility of divergent laser traps with biological material indicates the great potential of this new generation of laser traps in medical research and life science. Recently, the optical cell rotator technology was implemented on the basis of adaptive optics, allowing to dynamically reconfigure the optical trap during operation and adapt it to the sample. Cell sorting. One of the more common cell sorting systems makes use of flow cytometry through fluorescent imaging. In this method, a suspension of biologic cells is sorted into two or more containers, based upon specific fluorescent characteristics of each cell during an assisted flow. By using an electrical charge that the cell is trapped in, the cells are then sorted based on the fluorescence intensity measurements. The sorting process is undertaken by an electrostatic deflection system that diverts cells into containers based upon their charge. In the optically actuated sorting process, the cells are flowed through into an optical landscape that is 2D or 3D optical lattices. Without any induced electrical charge, the cells would sort based on their intrinsic refractive index properties and can be reconfigurability for dynamic sorting. An optical lattice can be created using diffractive optics and optical elements. On the other hand, K-Ladovac al. used a spatial light modulator to project an intensity pattern to enable the optical sorting process. Caixior and E.G. Grier applied holographic video microscopy to demonstrate that this technique can sort colloidal spheres with part per thousand resolution for size and refractive index. The main mechanism for sorting is the arrangement of the optical lattice points. As the cell flow through the optical lattice, there are forces due to the particle's drag force that is competing directly with the optical gradient force from the optical lattice point. By shifting the arrangement of the optical lattice point, there is a preferred optical path where the optical forces are dominant and biased. With the aid of the flow of the cells, there is a resultant force that is directed along that preferred optical path. Hence, there is a relationship of the flow rate with the optical gradient force. By adjusting the two forces, one will be able to obtain a good optical sorting efficiency. Competition of the forces in the sorting environment need fine-tuning to succeed in high-efficient optical sorting. The need is mainly with regards to the balance of the forces. Drag force due to fluid flow and optical gradient force due to arrangement of intensity spot. Scientists at the University of St Andrews have received considerable funding from the UK Engineering and Physical Sciences Research Council for an optical sorting machine. This new technology could rival the conventional fluorescence-activated cell sorting. Evanescent fields. An evanescent field is a residue optical field that leaks during total internal reflection. This leaking of light fades off at an exponential rate. The evanescent field has found a number of applications in nanometer resolution imaging. Optical micromanipulation are becoming ever more relevant in research. In optical tweezers, a continuous evanescent field can be created when light is propagating through an optical waveguide. The resulting evanescent field has a directional sense and will propel microparticles along its propagating path. This work was first pioneered by S. Kawata and T. Sugihara, in 1992, who showed that the field can be coupled to the particles in proximity on the order of 100 nanometers. This direct coupling of the field is treated as a type of photon tunneling across the gap from prism to microparticles. The result is a directional optical propelling force. A recent updated version of the evanescent field optical tweezers makes use of extended optical landscape patterns to simultaneously guide a large number of particles into a preferred direction without using a waveguide. It is termed as lensless optical trapping. The orderly movement of the particles is aided by the introduction of Ronchi ruling that creates well-defined optical potential wells. This means that particles are propelled by the evanescent field while being trapped by the linear bright fringes. At the moment, there are scientists working on focused evanescent fields as well. Another approach that has been recently proposed makes use of surface plasmons, which is an enhanced evanescent wave localized at a metal dielectric interface. The enhanced force field experienced by colloidal particles exposed to surface plasmons at a flat metal dielectric interface has been for the first time measured using a photonic force microscope, the total force magnitude being found 40 times stronger compared to a normal evanescent wave. By patterning the surface with gold microscopic islands, it is possible to have selective and parallel trapping in these islands. The forces of the latter optical tweezers lie in the femtonewton range. The evanescent field can also be used to trap cold atoms and molecules near the surface of an optical waveguide or optical nanofiber. Indirect approach Ming Wu, a UC Berkeley professor of electrical engineering and computer sciences, invented the new optoelectronic tweezers. Wu transformed the optical energy from low-powered light-emitting diodes into electrical energy via a photoconductive surface. The idea is to allow the LED to switch on and off the photoconductive material via its fine projection. As the optical pattern can be easily transformable through optical projection, this method allows a high flexibility of switching different optical landscapes. The manipulation tweezing process is done by the variations between the electric field actuated by the light pattern. The particles will be either attracted or repelled from the actuated point due to its induced electrical dipole. Particles suspended in a liquid will be susceptible to the electrical field gradient. This is known as dielectrophoresis. One clear advantage is that the electrical conductivity is different between different kinds of cells. Living cells have a lower conductive medium while the dead ones have minimum or no conductive medium. The system may be able to manipulate roughly 10,000 cells or particles at the same time. See comments by Professor Kishan Talakia on this new technique, K. Talakia, Nature Materials 4, 579 Euro 580 News and Views. The system was able to move live E. coli bacteria and 20 micrometer wide particles, using an optical power output of less than 10 microwatts. This is 100,000th of the power needed for direct optical tweezers. Optical binding when a cluster of microparticles are trapped within a monochromatic laser beam, the organization of the microparticles within the optical trapping is heavily dependent on the redistributing of the optical trapping forces amongst the microparticles. This redistribution of light forces amongst the cluster of microparticles provides a new force equilibrium on the cluster as a whole. As such, we can say that the cluster of microparticles are somewhat bound together by light. One of the first evidence of optical binding was reported by Michael M. Burns, Jean-Marc Fournier, and Gennady Golovchenko. References. External links, Optical at DMOZ.